comprehensive guide to HPLC. Warning: this video includes everything you need to know about HPLC. Once you watch this video, you'll be dying to watch the next series. Let's see how HPLC is configured. Generally, HPLC is configured with mobile phase, a pump, which is also called a solvent delivery module, injector, which can be either manual injector or auto sampler, a column, a detector, and a CDS, chromatography data system. Once each module is configured into an HPLC system, it can show how the flow goes through a HPLC. The mobile phases drawn to the pump pass through vacuum degassing unit, while it removes out dissolved gases in the mobile phases. The degassed mobile phases are mixed in a right composition rate depending on the application. Then the injector loads and injects the sample, and the pump delivers the sample in injector to the column with the mobile phases. The samples are separated into individual components through various chemical interaction with solid phase in the column. The detector then converts the concentration of each component into electrical signal. Finally, the signals are shown as a chromatogram by the chromatography data system. Let's look into mobile phase in detail. What is the mobile phase in chromatography? The mobile phases are used to move the analytes to the column. And it's a key step to select the appropriate mobile phase in the chromatography because it can impact on separation as well as the retention time. The mobile phase selection differs by HPLC separation modes. In normal phase chromatography, the non-polar mobile phase and the polar stationary phase are used. So, the non-polar compounds get eluted first from the HPLC column, then polar compounds in order. In reverse phase chromatography, the separation of the analytes is based on non-polar interaction. Generally, the mobile phase is more polar than stationary phase, and the more polar compound is eluted first from the HPLC column. In ion exchange chromatography, the separation depends on ionic interactions between ionic and polar molecules, and the aqueous salt solution is commonly used as mobile phases. It's generally to use buffer solution to adjust the strength and selectivity of the solvent by managing pH and salt concentration. Size exclusion chromatography, SEC, also called gel permeation chromatography. The analytes are separated according to their molecular size. The mobile phase is an organic solvent, non-aqueous solution that can dissolve the sample and maintain consistent viscosity at operating temperature. Keeping in mind, there are general requirements for mobile phase that can affect the selectivity. First, purity. All solvents should be pure in HPLC grade to have minimal absorbance in the UV. The mobile phase viscosity should be as low as possible. The solvents must be non-corrosive to HPLC system components. The solvents must be concerned with the health and safety risks. The solvents should be completely mixed each other in all proportions. And there is the solvent miscibility chart you can refer to, which shows the miscibility between general solvents for HPLC. And the refractive index should be considered in case of use of RI detector. If the RI of mobile phase is the same as one of the analytes, no detection will occur. RID can detect the analytes as long as their RI is different from that of the mobile phase. The mobile phase, without sample, must transmit sufficiently at the wavelength used for detection. This relates to the UV cutoff that is required for the use of UV detector. The UV cutoff of mobile phase should be lower than the one of the analytes. Mobile phase selection for HPLC seems very challenging, but if we handle with the most commonly used HPLC mode, RPC, we can narrow down the options to focus on the conditions which will give us the highest likelihood of success. Because there are typically used solvents for reverse phase chromatography. And we have to be aware of one more concept: elution strength. Elution strength, also called solvent strength, refers to the ability of a solvent to elute solutes from a column. Putting these solvents in order of elution strength, the water is a weak solvent and organic solvents are strong. Elution strength is related to its polarity. If you use the mobile phase as weak solvent, the nonpolar compounds are retained in a column longer. But if you use the mobile phase as strong one or increase the amount of organic solvents, the nonpolar compounds are relatively eluted earlier. Thus, the mobile phase strength depends on both the choice of organic solvent and its amount in the mobile phase. This graph shows the relative elution strength for different solvents. 50% methanol has the same elution strength as 40% acetonitrile or 30% tetrahydrofuran. Preparing mobile phase, we need to consider the pH of mobile phase and sample. When the sample contains ionizable compounds, the pH of the mobile phase will determine the degree of ionization of analyte, which affects retention as well as selectivity. If the mobile phase pH is near to the pKa range of sample, the small changes in pH can lead to dramatic changes in retention. At low pH, acids will be more retained, whereas base will be more retained at high pH. This is why the pH of mobile phase has to be correctly adjusted to control the ionization state of analyte for desired retention, resolution, and peak shape. For acidic compounds, if the pH is below pKa, the analyte gets more hydrophobic and retained longer. At pK range, the small changes in pH will lead to large changes in retention, and so is the resolution. And if the pH is above pKa, the analyte gets less hydrophobic and eluted faster. For basic compounds, it works vice versa. The analyte gets less hydrophobic and eluted faster if the pH is below pKa. And the analyte gets more hydrophobic and retained longer if the pH is above pKa. The most important thing to decide the pH of the mobile phase is that its pH must be at least 2 units above or below the pKa value for maximum analyte stabilization. To control the pH of mobile phase, we use the buffer and additives. A buffer solution is an aqueous solution, which maintains the pH of a solution within a narrow range by suppressing or pairing ionization of analytes in order to achieve reproducible separation and retention. Let's say there is water-based mobile phase, and if the acid is added, the pH will be lower and turn to acidic. But if we have buffer in the mobile phase, although we add acid, the pH of mobile phase will be stable. Adding base will work vice versa. There are certain recommendations for buffer selection. These table provides commonly used buffers and additives, including pH range and pKa value. For the most effective buffering, a buffer should be used within plus or minus 1 pH unit of the buffer's pKa. The most popular buffers for HPLC with UV detection are phosphate and acetate due to their UV cutoff. Finally, keep this consideration in mind when selecting buffers. Buffer concentration. Increasing buffer concentration leads to faster elution of polar molecules, but higher concentration increased viscosity, resulting in high column back pressure. A concentration range of 10 to 50 millimoles is normally adequate for most applications. Degradation of buffer. Some buffers degrade with time, and their UV absorbance increases. Mobile phase containing these buffers should be made fresh. UV cutoff values. Buffer should be transparent enough at the wavelength of detection. The UV cutoff of commonly used buffers is from about 230 to below 200 nanometer. Buffer should be compatible with the mobile phase. You need to prevent the precipitation of buffer in the system. A test tube test should be conducted and will determine the buffer precipitation. For use of LC-MS, Volatile buffers should be selected according to the recommendation. For the use of silica-based column, pH range should be adjusted within pH 2 to pH 8. Want to learn more about chromatography? Please stay tuned on Young in Chromas channel.